Reflections of absolute value functions. When reflecting the graph of an absolute value function, f of x, across the x-axis, it's given by negative f of x. So if we have the absolute value of the quantity x minus 2, and then we reflect it over the x-axis, our new function g of x becomes negative f of x, or negative absolute value of the quantity x minus 2. Now let's talk about reflecting the graph across the y-axis. This occurs when, instead of the negative being outside of the entire function, it's just out in front of the new variable. Instead of x, it's negative x. So in our case, again, we still have f of x is equal to the absolute value of the quantity x minus 2. Here's what it looks like. And then if we substitute negative x in for this new function h of x, which is f of negative x, it'll become the absolute value of the quantity negative x minus 2. Now we can actually factor out a negative 1, but keep it inside of the absolute value, and we end up with negative 1 times x plus 2. And then if we were to use a property of absolute value with a product, which says if you're taking the absolute value of the product of two numbers, it's equivalent to the absolute value of each number or term. So we're going to have the absolute value of negative 1 times the absolute value of x plus 2. Well, the absolute value of negative 1 is positive 1, so that's why there's the coefficient of 1 here, and we're left with the absolute value of the quantity x plus 2. Reflecting the graph of f of x across the x-axis is given by negative f of x. This means that we're taking our original function f of x and we're making the entire thing negative. So when f of x is equal to the absolute value of the quantity x minus 2, negative f of x is equal to negative the absolute value of the quantity x minus 2. So if we substitute negative 2 in to our function, we would get negative 2 minus 2, which is negative 4. Its absolute value is positive 4. So like right about here would be that point. If you substitute negative 1 in, negative 1 minus 2 is negative 3. Its absolute value is positive 3. So that's why we have this point right here. And then its corresponding point in g of x, we're still going to execute negative 1 inside of here. Negative 1 minus 2 is negative 3. Its absolute value is positive 3. But now we're making it negative because of this sign that's out in front. So that's why this point is way down here. So if we substitute 0 in, we'll get negative 2. Its absolute value is positive 2. If we substitute 0 in here, we get the negative absolute value of negative 2. Absolute value of negative 2 is positive 2, but then we make it negative. So we have these 2 points corresponding. You see how we're reflecting it across the x-axis every time. The same distance from the x-axis to the original point is provided from the x-axis to the new point. Reflecting the graph of f of x across the y-axis is given by f of negative x. So if our original function is f of x, which is equal to the absolute value of the quantity x minus 2, and h of x is equal to f of negative x, which is equal to the absolute value of the quantity negative x minus 2, which we've shown is equivalent to absolute value of negative 1 times x plus 2 when you factor out that negative 1. And then we know by the rules of absolute value, you can, when you have the absolute value of a product of two terms, you can take the absolute value of each term and multiply them together. And the absolute value of negative 1 is 1, and the absolute value of x plus 2 is x plus 2, which makes these two expressions, absolute value expressions, equivalent. Now if we look at the graphs of our original function f and our reflected function h right here, we can see that, for example, the vertex originally was at 2, 0, and now after you reflect it across the y-axis, the vertex now is going to be negative 2, 0. So the y-coordinates all stayed the same, but the x-coordinates switched signs. So that's how we get from f to h. Now let's try an example where we are graphing reflections. We're going to let f of x be equal to -3 times the absolute value of the quantity x minus 3, and then plus 9. Its graph is currently displayed. The functions g and h are given by g of x is equal to negative f of x, and h of x is equal to f of negative x. Carefully sketch the graphs of g and h on the grid to the right, and also write the formulas for g and h that do not involve f, and otherwise put them in terms of the absolute value. So let's first get started with sketching the graph of g of x. G of x is equal to negative f of x. That means for every input value that we put in, we're going to get the opposite y value as our output. So for example, at 1 in f, we're at 3. So in g, when we're at 1, we're going to be at -3. And then 2, f is at 6. So then g of 2 will be -6. f of 3 is 9. So g of 3 is going to be -9. And we can see how the graph of g of x is going to look. So let's connect our dots with an approximate absolute value function. Okay, so now let's also write the formula for g. So g of x is equal to negative f of x. So we're going to take all of this and stick it inside a set of parentheses. So we have a -3 absolute value x minus 3 plus 9. And we have to take this -1 that's out in front here, and we need to distribute it to both terms that we have. So this will make g of x be equal to +3 times the absolute value of x minus 3, and then minus 9. And notice at 3, -9, that is indeed our vertex of this absolute value function. And now let's do the same for h of x. H of x is equal to f of negative x. This means that we are going to reflect the function f about the y-axis. So the point at 0, 0 is going to stay there, but the point at 6, 0 is now going to go through -6, 0 when it's reflected across the y-axis. And this point up here at 3, 9, well, that, when we reflect it across the y-axis, is going to go through -3, 9. So the graph of this function is going to look something like this. Oh, and it does overlap right here, but then it just continues to go on. So here's h of x, and now what's the actual formula or function for h? So h of x equals f of negative x. That means wherever an x appears in the original function, we're going to substitute in a negative x. So we still have the -3 out in front, then we have the absolute value of -x minus 3, and then plus 9. Now remember, by the rules of absolute value, we can then take a -1 out of both of these two terms. So we still have the -3 out in front, but then inside the absolute value, we're going to factor out a -1. When we do that, we will have x plus 3, and then the plus 9 is still there. And now since the absolute value of a product is equal to the product of the absolute values, we can then write this as -3 times the absolute value of -1 times the absolute value of x plus 3, and then plus 9. And now when we simplify this further, we're going to get still the -3 out in front, then the absolute value of -1 is +1, so we don't have to rewrite that, and we have the absolute value of x plus 3, and then plus 9. So here's our h of x function that we just graphed. And here are the solutions to this example, and the graphs that appear, as well as the functions that we have for g of x and h of x do indeed match the functions that we found when we worked through the problem together. Here's another example. Let f of x be equal to the absolute value of x minus 3/4 times x. Notice 3/4 is written as a decimal, which is 75/100, plus 1. Its graph is displayed. The functions g and h are given by g of x is equal to negative f of x, and h of x is equal to f of negative x. We first have to sketch the graphs of g of x and h of x on the grid to the right and label each one. Then we need to write formulas for g and h that do not involve the function f. Alright, let's get started. So first we're going to do g of x, which is equal to negative f of x. That means you still substitute x in there, but whatever the output is going to be the opposite output. And because the outputs are becoming opposites, we're doing a reflection across the x-axis. So we're going this way. So the original point that's a vertex at 0, 1 is going to end up being at 0, -1. And this point at 4, 2 will be at 4, -2. And then this point that's at -1, 2 3/4, or 2 75/100 is going to go down to -2 75/100, or -2 3/4 down here. So our graph of g of x is going to look something like this. So we have g of x. And we can also write a formula for g of x. G of x is equal to negative f of x. So that means we have this -1, and we're going to multiply it by this entire f of x function. So that's the absolute value of x minus 3/4, so that's 75/100, x plus 1. And from here, we're going to take this -1 and we are going to distribute it to all three of the terms that we have in this set of parentheses. And when we do that, g of x is now going to equal the negative absolute value of x plus 3/4 x, or 75/100 x, minus 1. So here's our final equation for g of x. And we did the graph of it when we began. Now let's look at h of x. H of x is equal to f of negative x. What that means is we are reflecting our original f of x function across the y-axis. That means our x values that are originally positive are going to become negative, and they will yield the same output. So our original point of 4, 2 will become -4, 2. So that point will be right about here. The point that is at 0, 1 will continue to be at 0, 1 because you can't change the sign of the x-coordinate 0. And then this point at -1, 2 3/4, that's going to now be +1 and 2 3/4. So the graph of this function is going to look something like this. This is h of x. And now we have to determine the formula for h of x that does not involve f. Well, f of negative x means we're going to take f of x and write it, but wherever we have an x, we're going to put a negative x in its place. So we have negative x minus 75/100 negative x, and then plus 1. Well, we have the subtraction of a negative here, so this is going to change to a plus sign, and then the plus 1 stays the same. And now, because we have this negative inside of the absolute value, we can rewrite it as the absolute value of -1 times the absolute value of x, and the absolute value of -1 is +1. So I'm going to erase it to save some room. So therefore h of x is going to equal the absolute value of x plus 75/100ths x plus 1. And here are the solutions that we found for negative f of x, which is equivalent to g of x. It is equal to the negative absolute value of x plus 75/100ths times x minus 1. And h of x, which is f of negative x, is equal to the absolute value of x plus 75/100ths times x plus 1. And the graphs that appear in the coordinate plane do indeed match the graphs that we drew.